Something strange appeared near Mars, and it was not supposed to happen like this. The James Webb Space Telescope turned its golden eye toward the red planet, and within moments, the data coming back looked wrong. One region was darker than it should have been. Another was glowing with far more heat than expected. And the thin space around Mars suddenly felt less empty than scientists had assumed. What Webb captured did not just give us a better picture of Mars, it reopened a mystery that has been haunting planetary science for years. And the deeper you look, the stranger it gets. To understand why this matters, you have to remember what James Webb was built to do. This telescope was designed to look far beyond our solar system, into ancient light that has been traveling for billions of years. It was made to detect things so faint that most telescopes would never even notice them. Distant galaxies, hidden stars, alien worlds crossing the faces of suns you will never see with your own eyes. Mars is the opposite of that. Mars is bright, very bright. In infrared light, the kind Webb sees best, Mars can be almost blinding. So from the start, this was not a normal observation. It was risky. If the settings were wrong, Mars could flood the detectors and ruin the image. That is how powerful Webb is. It can see the birth of galaxies, but it can also be overwhelmed by a planet in our own backyard. That is why the first Mars observation was so important. It was not just about getting a pretty picture. It was a test. Could Webb, the most advanced space telescope ever built, turn toward a bright nearby world and still pull out fine details from its surface and air? NASA, the European Space Agency, and the Webb science teams wanted to know if this observatory could become something more than a deep space machine. They wanted to know if it could help solve questions much closer to home. Questions about dust, water, heat, carbon dioxide, clouds, maybe even methane. And when you hear methane on Mars, you should pay attention, because that one word has started arguments that have lasted for decades. Mars is not just another planet in the sky. It is the planet people keep returning to in their minds. If humans ever live somewhere beyond Earth, Mars is the place most people imagine first. It has seasons. It has polar ice. It has volcanoes bigger than anything on Earth. It has canyons so wide they make our own greatest landscapes look small. Long ago, it had rivers, lakes, and maybe even seas. You can still see the scars of flowing water cut into its surface. So every new clue matters. Every strange signal matters. Because hidden inside the rocks and air of Mars is a much larger question. Did this world ever get close to becoming alive? Now imagine the scene. A telescope sitting far from Earth, nearly 1 million miles away, balanced in a special place in space where it can stay cold and stable. That location lets Webb stare with incredible precision. When it looked at Mars, it was not taking an ordinary snapshot. It was gathering light at different infrared wavelengths. In simple terms, it was not just seeing Mars, it was peeling Mars apart layer by layer. Some wavelengths reveal reflected sunlight, others reveal heat, others carry chemical fingerprints from the atmosphere. To the human eye, that might sound abstract. To scientists, it is like hearing a whisper inside a locked room. And then the data arrived. The first set of Webb images focused on the eastern hemisphere of Mars. One image was dominated by reflected sunlight. In that view, familiar features could be seen. The Huygens crater, the dark volcanic region called Syrtis Major, the giant Hellas Basin, one of the biggest impact structures on the planet. So far, so normal. The planet looked recognizable, but the second image was the one that changed the mood. This one showed thermal emission, the heat Mars gives off. Suddenly, the planet was no longer just a red sphere with old scars. It became a map of energy. Warm areas glowed. Cooler areas dimmed. Day, season, angle of sunlight, and atmospheric behavior all started to show themselves at once. And that is when scientists saw something they did not expect. Hellas Basin looked darker than the land around it. That may not sound dramatic at first. A dark patch on Mars? So what? But in a heat-sensitive image, dark can mean something very different. It can mean cooler temperatures. It can mean the atmosphere is blocking the signal. It can mean the surface is behaving in a way that does not match the first guess. Hellas is huge. It is a deep basin left behind by a colossal ancient impact. Because it sits lower than much of the surrounding terrain, the air pressure there is higher than nearby regions. That should matter. But seeing it play out so clearly in Webb's infrared view was startling. For a moment, the image looked almost wrong. This is where things take a strange turn. At first glance, you might think Hellas was simply colder than the areas around it. But that was not the full answer. The darkness was not just about heat. It was about the atmosphere of Mars itself. As infrared light rose from the planet and moved through the air, carbon dioxide molecules absorbed part of that signal. In Hellas Basin, where the pressure is higher, that effect becomes stronger. Scientists call part of this process pressure broadening. The name sounds technical, but the idea is simple. The thicker the local air, the more the carbon dioxide changes the way light passes through. So Webb was not merely seeing the surface, it was seeing the atmosphere distort the picture. Think about what that means. A telescope built to look across billions of light years turned toward Mars and immediately revealed that even our neighboring planet can still trick us. A place we have mapped, orbited, landed on, and studied for generations still produced an image that made experts stop and say, wait, what exactly are we looking at here? That pause matters. Because science often moves forward in those moments of discomfort. When the first answer does not fit neatly and the data refuses to behave, Webb's Mars observation was supposed to be difficult because Mars is bright. But it became fascinating because Mars turned out to be layered, deceptive, and more dynamic than a simple photograph could ever show. Then came the spectrum. If the images were strange, the spectrum was even more revealing. A spectrum is what you get when you split light into many wavelengths and look for tiny dips and rises. Those patterns are chemical clues. Every gas leaves its own sort of fingerprint. Webb's spectrum of Mars showed strong signatures from carbon dioxide, carbon monoxide, and water. That alone was exciting because it proved Webb could read the Martian atmosphere in remarkable detail, but it also opened a door that researchers have wanted to walk through for years. If Webb can do this, then it may be able to hunt for far fainter ingredients too. Trace gases, seasonal shifts, small changes in the chemistry of the air, the kind of things that could tell us whether Mars is geologically active, chemically surprising, or hiding processes we still do not understand. And yes, that includes methane. But hold that thought for a moment, because the story gets even more complicated. Mars has always been a planet of mixed signals. Orbiters see one thing, rovers measure another. Telescopes on Earth pick up hints that later seem to vanish. A plume appears in one set of observations and disappears in the next. One mission finds seasonal behavior, another finds silence. It is like trying to understand an animal moving through fog, and you know it is there. You see tracks, you hear sound. But every time you think you have the full shape, it slips away. Webb stepped into that confusion with a major advantage. It sees in infrared with incredible sensitivity. It can separate wavelengths with precision that lets scientists detect subtle atmospheric effects that are difficult to isolate from the ground. But Webb also came with a new challenge. Mars was so bright that the team had to use very short exposures and special observing methods just to avoid saturation. In other words, the telescope had to blink quickly at the planet, like someone glancing at a bright lamp. Even so, the amount of detail was stunning. You would think that after all these years, Mars would be one of the easier worlds to understand. It is close. We have sent rovers. There. We have flown orbiters over it. We have studied Martian dust, storms, rocks, weather, ice, and seasons. Yet every time a better instrument arrives, Mars becomes less simple, not more. That is the real story here. Webb did not just sharpen an old picture. It revealed how much of the old picture was incomplete. And that is only the planet itself. Because when people talk about what Webb photographed near Mars, they are not just talking about the face of the planet, they are also talking about the space around it, the Martian system, the moons, the possibility of faint dust, hidden particles, tiny bodies too dim to see easily against the glare of Mars. This is one of the quiet reasons scientists were so interested in using Webb on the red planet. Mars has two strange little moons, Phobos and Deimos, and both of them remain deeply puzzling. Are they captured asteroids? Are they fragments from an ancient impact? Did Mars once have a ring? Could it form one again in the future as Phobos slowly spirals inward and breaks apart? Those are not small questions. They change the history of Mars. Phobos, the larger moon, is inching closer to Mars over time. One day, scientists believe it may be torn apart by the planet's gravity. If that happens, Mars could briefly wear a ring before the debris rains down or spreads out. Deimos, the smaller and more distant moon, is quieter, but perhaps even more mysterious. Its origin is still debated. Some of its properties resemble certain dark asteroids. Other clues suggest that story may be too simple. Recent missions have added pieces to the puzzle, but not the final answer. So when Webb looked near Mars, researchers were not only thinking about one planet. They were thinking about a whole system with loose ends everywhere. But here is the part nobody expected. Webb is better at this than many hoped. Scientists planning sensitive searches around bright planets knew there would be scattered light. They knew glare could hide faint objects. They knew the bright disk of Mars would make the nearby space hard to study. But Webb's optics and performance have been extraordinary. In simple language, it can pick out faint things, close to bright things, more effectively than some feared. That means the telescope can do more than watch Mars glow. It can help search the space around Mars with fresh eyes. Imagine what that means. A world we thought we knew. Two moons we still cannot explain. The possibility of debris, dust, or subtle features close to a bright planet. And now a telescope sensitive enough to make even familiar terrain feel uncertain again. This is where the mystery deepens. Because the real power of Webb is not that it produces dramatic pictures, it is that it catches contradictions. In one wavelength, a place on Mars may look bright. In another, it may look strangely dark. In a standard image, the surface may seem still. In a spectrum, the atmosphere suddenly becomes alive with hidden structure. A single observation can contain daytime warmth, evening cooling, seasonal contrast, surface mineral hints, cloud signatures, and gas absorption all tangled together. You are not looking at one thing. You are looking at many things at once. That is exactly why scientists were so careful with the first Mars results. Even NASA described the data as science in progress. That matters. It means the team knew the images were exciting, but also knew they had to be interpreted with caution. When a new instrument reveals a world in a new way, the first reaction is not always certainty. Sometimes it is humility. The telescope shows you something real, but you're still learning the language needed to read it. And just when you think the mystery is about a dark basin and a bright planet, another question appears. What if the most important thing Webb saw was not a feature on the ground at all, but a new way of tracking Mars through its air? That possibility is huge. Mars has one of the most argued overatmospheres in planetary science. Most of it is carbon dioxide. It is thin, cold, and harsh. But hidden within that larger blanket may be trace amounts of gases that appear, disappear, change with season, or collect in ways we do not yet fully understand. Methane is the most famous example. On Earth, methane is often tied to living things, but it can also come from geology. On Mars, even a small amount would be explosive news. Not literally explosive, but scientifically explosive. It could point to active chemistry underground. It could hint at ancient reservoirs being released. It could even reopen the biggest question of all. Was Mars ever alive? And could anything still survive there now? This is the cliff edge in the story. Because scientists have been chasing methane on Mars for years, and the results have been maddening. Some observations seemed to detect it. Others found nothing. Some teams reported local spikes. Others could not confirm them from orbit. The European missions around Mars brought important limits and fresh debate. The Curiosity rover made headlines with methane measurements near the surface. Then other observations seemed to challenge how that methane could exist without showing up elsewhere. It became one of those scientific mysteries that is almost worse than a clean unknown because the data keeps hinting at something but refuses to settle into a clear answer. Webb changed the mood, not because it instantly solved methane, but because it gave scientists another powerful way to look. If it can map atmospheric behavior and identify major molecules with such clarity, then the dream of using it to constrain trace gases becomes far more serious. Suddenly, Mars is not only a target of history, it is a live laboratory. And if weird things are happening in the air, Webb may be one of the best tools we have to catch them. Then comes the emotional peak of the whole story. The strangest part of this discovery is that the more clearly Webb sees Mars, the less fixed Mars becomes. That sounds backwards, but it is true. Better vision should remove mystery. On Mars, it often creates more of it. A simple color image of the red planet can trick you into thinking you are looking at a dead place, dry and finished, all its major stories written long ago. But infrared. Light tells a different story. Heat shifts across the surface. Carbon dioxide shapes the signal. Clouds and dust matter. Pressure changes the behavior of light. The planet is not silent. It is still reacting, still moving, still hiding information in plain sight. And when one region like Hellas Basin suddenly appears dark for reasons that mix altitude, pressure, gas absorption, and thermal behavior, you begin to understand how easy it is to misread Mars. A basin becomes a false cold spot. A bright region becomes a complicated blend of sunlight and heat. The thin atmosphere becomes a lens, a filter, and a mask all at once. Mars is not just a place. It is a layered illusion. That is why the title sounds so dramatic, and in a way, it deserves to. Scientists can explain parts of what Webb photographed, but the full meaning of those images reaches far beyond one neat answer. They can tell you why carbon dioxide likely darkened Hellas in that wavelength range. They can tell you Mars was close to detector saturation because it was so bright. They can tell you the spectrum clearly showed known molecules. But the harder question is, what all of this means when combined. How do you use these new infrared views to untangle the old methane debate? How do you separate surface effects from atmospheric effects with total confidence? How do you search the space near Mars for faint clues when the planet itself is blasting the detector with light? How do you read a world that keeps changing depending on the instrument, the season, and the scale? No one answer closes all of that. And then there are the moons. The moment you widen the story from the planet to the system around, the mystery expands again. Phobos and Deimos are among the oddest natural satellites in the inner solar system. They are small, dark, misshapen, and ancient-looking. For years, many scientists leaned toward the idea that they were captured asteroids that seemed to fit their rough appearance and low reflectivity. But later, evidence made the story less certain. Some orbital features do not fit a simple capture scenario very well. Some observations hint that they may instead be leftovers from a giant impact that once blasted material into orbit around Mars. If that is true, then Mars did not just survive violence in its distant past. It may have rebuilt part of its moon system afterward. Why does that matter here? Because when Webb looks near Mars, every faint feature, every subtle brightness pattern, every search for small moons or dust structures connects back to that deeper history. If Mars once had a debris disk, what traces might remain in its moons? If Phobos is on its way to destruction, what does that tell us about the future ring of Mars? If Deimos is not what we thought, what else about the Martian system have we oversimplified? This is the point in the story where a lot of viewers expect a giant answer, a hidden alien craft, a secret structure, a shocking signal nobody can decode. But the truth is more unsettling because it is more real. What Webb photographed near Mars was not a movie-style twist. It was a scientific trapdoor. The data looked familiar enough to make us confident, then strange enough to pull that confidence away. It reminded experts that Mars is still capable of surprising us, not because it is magical, but because it is complex. And complexity can be more haunting than fantasy. Think about the scientists themselves for a second. People like Geronimo Villanueva and the teams working with NASA, the European Space Agency, and the Space Telescope Science Institute are not easily shocked. These are people who spend their lives turning faint light into hard evidence. They know instruments can create artifacts. They know first impressions can be misleading. They know you do not declare a revolution because one image looks weird. And yet even they described parts of the Mars result with caution and interest that you can almost feel between the lines. The message was clear. Something important is here. We can see more than before. But interpreting it will take time. That cautious excitement is often where real discovery begins. Heidi Hammel and others involved in Webb's solar system work have long argued that this telescope is not only for the far universe. It can transform our understanding of nearby worlds too. Mars is the perfect example. It is bright, difficult, and scientifically rich. It forces Webb to do something challenging. But in doing so, it may reveal connections that other missions alone could not easily provide. Rovers tell us what is happening at one location on the ground. Orbiters give regional and global views. Webb adds a powerful infrared perspective from far away, a kind of wide but detailed chemical snapshot that bridges scales. Experts reacted strongly because Webb seemed to validate that promise almost immediately. The first observations showed surface details, atmospheric effects, and spectral features in a way that made future studies feel much more ambitious. Now, researchers can think about tracking regional differences over time. They can compare Martian seasons. They can look for subtle changes in dust and clouds. They can continue the search for trace species like methane and hydrogen chloride. They can combine Webb data with results from Mars, orbiters, and rovers to test whether mysterious signals are local, global, seasonal, or simply misunderstood. But agreement is not the same as certainty. Some scientists are more cautious about dramatic interpretations than others. That is normal. In planetary science, there is always tension between excitement and verification. One team may see a clue and say, this could point to active chemistry. Another may say, we need more observations before making that leap. One researcher may focus on atmospheric physics. Another may focus on surface composition. That is not a weakness of science. That is the process working as it should. The interesting part is that Mars keeps producing enough strange evidence to keep those debates alive. And nothing keeps debate alive like methane. If Webb one day helps pin down the methane question more clearly, the impact could be enormous. If methane is truly present in changing amounts, then something on Mars is making it or releasing it. That source could be geologic. It could come from water reacting with rock deep underground. It could come from trapped ancient material slowly leaking out. In the most dramatic case, it could connect to microbial life, though scientists would never jump there first without exhausting every non-living explanation. Still, even the possibility is enough to hold the world's attention. Not because people want fantasy, but because Mars is one of the few places close enough, real enough, and ancient enough to make the question feel personal. What if life almost happened there? Or what if it did happen and left only whispers? There is also the practical side. Future astronauts will not care about Mars only as a mystery. They will care about its weather, its dust, its seasonal cycles, and its chemistry. Understanding how heat moves across the planet matters. Understanding how carbon dioxide shapes the atmosphere matters. Understanding whether hidden gases appear in certain regions matters. Webb's ability to read Mars from afar could support that future, not by replacing landers and rovers, but by giving the big picture that local missions alone cannot provide.